Okay, so I can see this. Let me summarize a little bit where we were last time. We have been doing last time. And basically consider so-called maximal operator, the type which was studied a lot in Euclidean harmonic analysis, but we consider the discrete version of that, namely the following. So for the maxima, I put a star, and there is a parameter lambda, which is something a number bigger than 1. And then when you apply this to a function at x, and here x is a lattice point in ZB, you define this as a supremum of the lower radii, which is between lambda and 2 times lambda of the convolution of f with sigma lambda. Where sigma lambda is basically the normalized indicator function, the lattice points on a sphere of radius lambda, and essentially normalized is because in dimension at least 5, you can put a normalization factor of something like lambda to the minus b minus 2, and the indicator function of s lambda, where s lambda was just the set of lattice points in ZB whose lengths equal lambda, but maybe I'm writing if they length squared equal lambda squared. And then there was one observation, and then when we wanted to show some LP bound for this maximal function in terms of the LP bound of the function itself. And an observation was that you can measure the maximal function with the integral of some convolution by expanding basically the indicator function as an integral, like they usually do in analytic numbers. And what we got, the first important observation was that a lambda star f P norm is bounded by a constant times, and the normalizing factor, you can take a common normalizing factor, capital lambda to the minus b minus 2, since lambda is about, say, as capital lambda, times an integral from 0 to 1 of f convolving some Gaussian function. I think I use capital G in honor of Gauss, LP, PT, where this Gaussian was e to the minus 2 pi epsilon was like p, absolute value of x squared, and epsilon was a small modifying parameter set up to lambda to the minus 2, I-ish, and basically this kind of cuts off. So this function is supported where epsilon x squared is less than 1, so x is less than lambda, as we would expect somehow, because that is the scale we are considering. So that was just a basic observation, and then if you apply p equal 2, and then this is just a multiplier, you get that in particular we consider p equal 2, and then in this case there are 2 norms of the discrete spherical maximal function on this one scale is bounded by lambda to the minus b minus 2, and then here, since this is a multiplier, there are 2 norms bounded by that number of times the n infinity norm of the Fourier transform. So the key was to estimate the infinity norm of this times the norm of that. And then we were able to show that this was bounded by a constant, and then we get this estimate on one scale. lambda. And how did we prove that? Was basically we did a periodic decomposition. On each periodic we got a different estimate, and we could integrate those estimates. So basically, we choose a periodic section at level lambda, which basically simply means you consider all rationals with Q denominator less than equal to lambda, and A is relative prime to Q. Of course, A is less than equal than Q because it's what we said, the points on the torus around 0, 1. And basically, we decompose accordingly the interval 0, 1, such that around any ration we chose the set of points which is closest to that rational. So then the basic estimate was, and you have the T, which is of the form A over Q plus tau, is in the appropriate periodic, then already from Dirichlet principle or from other ways, easy to see that this tau is less than 1 over lambda times Q. And using this, we get the following estimate, using Poisson summation for the Fourier transform of the Gaussian. Basically, then the key estimate was that this was bounded by a constant, and then it was coming after decomposing the sum mod Q, a Gaussian sum, normalized Gaussian sum appeared, which is estimated by the standard cancellation Gauss sum. So you gain a factor of Q to the minus D half, and then you have this factor. And then there was something relatively complicated, which was coming from Poisson summation, a sum over L in CP. And then what we had, the Euclidean Fourier transform of the Gaussian, which is explicit, and we put the absolute value of that, and that comes out something based on constant epsilon over epsilon squared plus tau squared, maybe times QC and sub squared. And then we could show that this was bounded by 1 because the way we set up our parameter, this is at least a constant, so this is measured just by a geometric series, which is bounded. So you can forget that, and now you can integrate these terms on each interval, you can sum it up, and everything would be bounded, and that's how we prove that this whole estimate would be bigger than 1, because what you have to do, first you integrate in tau to integrate on one period, and then you have to sum in all A's and Q's. So here, if you sum in A, that was QA, so you Q to the minus E half plus 1, and then you sum in Q, and that would be still bounded if these at least 5. But the reason I wrote this up, because we want to use the main term here to get more precise estimate to get from one scale to all scales, at least in the R2 case. So this is the most important one, and let me mention what we can see from this, how the property, whether T is close to a rational with small denominator, comes up. So in this sum, there is one L which is closest to this point Q times C, let's say it's integer part. So using this number theoretic notation that the point minus this integer part we denote it, right? So if we use the notation, let's say, which they often be numbers in one higher dimension. So using this notation, we can estimate this further. And let's leave out the main term, And the main term is when this the denominator is as small as possible, and that is when you have the fractional part, the length of the fractional part of cube C. So that's just one term. And maybe I just put a C instead of this pi over 2. Now, if we sum the rest, if you sum the rest of the terms, every other term here is bigger than a constant. So if you sum that, then the main term will dominate. So then basically you have just this term for the rest of the sum. And then if you use that an exponential is decaying faster than any power and you choose the right one, you can basically cancel out this power. So what you really get for the remainder term is something like the following. So if you call this for sin, so this is gone for the rest of the term. If you call this something like gamma and use that e to the minus gamma is less than equal to gamma to the minus d over 4 times a constant, because this is at least bigger than some of these numbers, it's roughly bigger than 1. And if I use the d over 4 power, then maybe I write instead of this. Let me put it this way. And I could promote that basically what I want to say here, if you use all the other L's and you put this part here, then these two terms cancel out. So let's see. Yeah, it's fine. And then these terms cancel out if I use the d over 4 power, so the constant might depend on d. But then I get something like an epsilon, epsilon to the d over minus d over 4. And epsilon to the minus d over 4 is lambda to the d over 2. So if I so this gives a contribution. If I plug this error term into the integral, what I have here into the integral, what I have here, I basically on every interval, so the lengths of the intervals are less than 1, on every interval, you can use this uniform estimate, and then in the summing AN2 would be bounded, so this would give an error term to the whole contribution of just lambda to the d over 2, but then I have a normalizing factor, lambda to the minus d minus 2, so this gives an error term in the whole expression, lambda to the minus d over 2 plus 2, which is less than equal lambda to the minus 1/2. And kind of, in the rest of the calculation, this error term won't really matter. So,
sorry, I don't understand. What happened here?
So basically, I use this. So if I solve for the rest of the L's,
what is the estimation for the fraction epsilon over epsilon squared plus tau squared? What is the
yes.
What estimate do you use?
For this is bigger than a constant. Even if and actually to be
Which one? Just that fraction?
Yeah.
I mean, we have a lambda to the minus 2.
Yeah, I mean, we have this estimate that even if I multiply with this q squared, it is bigger than a constant.
Mm-hmm.
That's what we used last time, because what the, so That is how it was. That's what I missed. Yeah, that's what I missed. Because normally it was C minus L over Q, so there's a cube C minus L and there's a cube squared. So this forcing was bigger than a constant. I think it was bigger than 1/2. I mean, so now if you think of this forcing as gamma, you have e to the minus gamma, and I replace the gamma to the minus d over 4. And then actually that was my problem, that the q cancels as well, because q squared. So if you take to the minus d over 4 power of that, then you get a q to the d half, it cancels this q to the d half. So we don't even have this q to the d half. So this whole term cancelled, all you have is just epsilon to the minus d over 4, which is lambda to the d half. So this whole error term, you have a uniform error term, lambda to the d half. So that is a trick to get rid of the whole tail of the sum. Okay, so we just use this simple estimate that e to the minus gamma to get rid of all these terms. Now, since you integrate this on the unit interval, the whole integral will contribute just this much. Now, if we compare it against the normalizing factor, how much contribution you give into the L2 estimate, you get at most this much. Lambda to the d half and lambda to the minus d plus 2. Lambda to the minus d half plus 2, which is lambda to the minus 1/2. So, this is just an observation that what.
Won't we need to sum it in gamma?
I'm sorry?
Won't we need to sum it in Q in the end, in the error term? Don't we need to sum it in Q?
Yeah, but you integrate, you sum of the integrals on these intervals, and the total length of the intervals is 1.
Okay.
So then the total contribution, if you have a uniform estimate, that is just bounded by the whole. Yeah. So, all right, so let's keep that in mind. And now let's use a more precise estimate. And to do that, let's introduce some certain sets and some notation. So that J bigger than or equal than 1. And I introduce a denominator Q sub J, which is the least common multiples of all q's up to 2 to the k. And I will explain why do I introduce this. Now, it's a little calculation. How large is this q sub j? But from the prime numbers theorem, you can certainly say that q sub j is about e to the 2 to the j. But what I will use is, which is easier to see. So if you want to think about this, what is the prime factorization of that? Well, which prime can appear? Prime can appear up to 2 to the j. And then how large of a power of a prime appears here? Well, the largest power, which is still less than 2 to the j. So it's something
So
like
that's 2 to the 2 to 4 to the 2 to the j.
A sub p, where this p to the a sub p is just about 2 to the j. And then by the prime, so all these terms are multiplied by 2 to the j, and how many primes you have 2 to the j over j. So if you think about this, this will be bounded by essentially e to the 2 to the j, but certainly if I choose something larger than e. So I will keep this in mind. Now, okay, so that's later we will use. And then, so what is the point here? The point here, if you take the grid of gap length 1 over q to the j, so you take this grid, c to the d, that will contain all the other grids with gap length 1 over q, where q is less than 2 to the j because it's a divisor. So for example, if I take a grid like, so let's say this is, so this is q to the, this is like 6, of course, it will contain the grid of size 1/2. So, and why am I doing that? Because now I will define some neighborhood of this grid which is the separative sum of this grid plus some small cube plus a small cube. So I will put a small cube around each lattice point. And the cube of size 1 over 2 to the k minus j, where k is a much larger parameter than j, and 1 over j to the d. There we will set this up so that k would be bigger than something like plus 2. And then this would imply that these little squares would be disjoint. So what I'm doing, I'm avoiding a neighborhood of all lattice points, the denominator q, where q is less than 2 to the j, by kind of putting all these lattices within one fixed lattice, by taking the least common multiple. So basically what I want to get, if a point is outside, so this is the Minkowski sum, so that means that you translate this cube around each lattice point. And what I want to show, if you're outside this, then you have a non-trivial better estimate of the Fourier transform of the lattice points on the sphere. And not just that, whatever the contribution of these points to the spherical maximal function, you will have a gain, and you can use that gain by using some kind of resolution of the function of the Fourier transform of the function. You use this estimate to work. So this implies my other setup, the little bit of thinking that 2 to the k minus j is much bigger than q, so j is still, so then these are indeed disjoint. So we set up, and then these neighborhoods, and then we will have the following key estimate. Okay, so let's call this first level, and that would be a key estimate. So again, dimension of this 5. Maybe I'll put it this way, k minus 2, which is the same relation that we see there. Then, first of all, which we will use for other things, not just for the maximal function, if c is not in here, then the Fourier transform of the lattice points on the sphere, normalized, will satisfy a non-trivial estimate. Of course, it's always less than equal than a constant because it's normalized, so the trivial is a constant. But now you will have a gain, and you will have the gain 2 to the minus j, j to the minus 1. And surprisingly enough, 2 to the minus j over 2, actually, j to the minus 1. Surprisingly enough, the j to the minus 1 will be important. In dimension 5, without that, things wouldn't work out. But what we would need, so this is this tells you the constant O, where for 2 to the k as an equal number. So this tells you a concentration of the Fourier transform into this set, which is just neighborhoods of the lattice points. Not lattice point, but of the grid of but in the maximal function, instead of like an estimate for one fixed lambda, you always have to replace that with the integral of this g dx and c. But now I restrict to the complement. So I consider this function, which is supported on the complement, and I take the infinity norm of that and integrate, and I still will have the same same estimate. So this is the key lemma. So notice that without this restriction, we would just have an estimate with a normalizing factor. And so here, the scalar would be okay. So lambda to the minus d minus 2 is 2 to the minus k d minus 2. So that's the second important estimate. Now, of course, this one implies that one because sigma lambda hat is majorized by the integral GT hat, and when C is not in this region, that it's majorized by the integral of this one because it's very infinitely long, so it would include C. So as a note, now this looks strange. So let me compare it for a second with the Euclidean case, where you have a concentration of the Fourier trans in the neighborhood of the origin, and by these parameters kind of set up more or less the right way. So the note, so kind of the corresponding thing in the Euclidean case. So think of sigma under just a normalized surface area measure on the sphere of radius lambda. So the Euclidean case, so on RD, it is well known, at least in dimension 3, or even dimension 2 is true, that the continuous Fourier transform of sigma lambda hat is sigma continuous lambda c, because you kind of change variables. So this is normalized measure on the sphere of radius lambda, which is by stationary phase bounded by 1 plus lambda c to the minus d minus 1 over 2. So that is less than, if you take at least minus 1/2. Okay, so now in the case when lambda is about 2 to the k, and C is of a cube centered at the 0 2 to the j minus k, which means that C is bigger than 1 over 2 to the j minus k, 2 to the minus j minus k. This means that lambda c is bigger than 2 to the j. So by this, you get the estimate 2 to the minus j/2, which is kind of the same thing. We have an extra j to the minus 1 because we assume something stronger, actually. A little bit stronger than just like being away from the origin. We are being away from a lot of lattice points. So this is the analog of the concentration of the Fourier transform at the origin for the continuous case, and that is the discrete kind of analog of that concentration. And that is the basis for many, many things which you can prove in the discrete case, which is somewhat analogous to some theorems in the Euclidean case. The scalar maximum is just one example. Okay, so we will use a little lemma, and that's an elementary exercise in elementary numbers. I need you to work it out. So a little lemma. So for any exponent bigger than 1, we will use the following fact. Now, if you sum q to the minus r, of course that is bounded because r is bigger than 1. But for all q's which does not divide q sub j, so does not divide the least common multiple of all q's up to j, Of course, this q has to be bigger than 2 to the j, otherwise, of course, itself would be included. So clearly, this sum is less than sum of q bigger than equal to 2 to the j, q to the minus r, which would be already bounded by 2 to the minus j, r minus 1. But then you get a little bit more, because this is a smaller set of q's. Okay, so we will use this little estimate in proving, in getting that extra gain. So the hint here is if q does not divide qj, then there are two possibilities. Either it has a large prime divisor, which is a prime divisor bigger than 2 to the j, or there exists a small prime divisor, but it contains a large power of it. P to the sum a divides q, where p to the a itself is bigger than 2 to the j. And then you can just sum in both cases. So in this case, you write q as p times q1, and in this case, you write q as p to the a times q1 and sum separately in p's and the q's and use the prime numbers. And with the primes up to primes of size about n is about n over log n. And this 1 over log n gives you the log 2 to the a, give you the extra j to the minus 1. So okay, so after these preparations, we can now prove this lemma, and from this lemma, we can prove the discrete spherical maximals, and we have two cases of that, which is still will be an essentially simpler proof than what we gave originally with sine and so to use the original formula, that this formula, and then of course we decompose the integration into integral of the major arcs. And under this, and then we will decompose both the summation and the integration into two parts. So this whole sum of integrals we decompose into three sums. So we start with so into the k, and we will write, because we will write this expression a number of times, we're simply mkf. So the maximum function attached to scale to the k, like left. And then,
sorry, I don't. What did you just say here? Let's denote that one as m. Oh, that's a notation.
This is much simpler than this
Not
notation. I
okay.
will write later a number of times, and I don't want to write this so many times when I do the resolution later. But at this point, k is fixed. So at this point, it doesn't matter too much. So maybe it was unnecessary. So by that formula, this is bounded by the integral of this L infinity norm of the Gaussian. But So maybe I just write it down first. So this is the normalizing factor under the minus d minus 2. And then there was some in Q and A and the integral on the major arcs of well, it's not quite what I want to say, to be honest. Instead of that, what I want to say is the left side of the expression on the second part of the lemma, so the left side. And then this is just the integral. Is equal times the sum of three terms. And the first term is coming from those q's which does not divide qj. Okay, so S1 will be the sum over all q's which does not divide qj. And in this case, we will just use the uniform estimate, what we had yesterday, so we don't need to use any finer estimates. So, okay, now I kind of numbered the boards, so maybe I can start. So some q does not divide qj, and I use the uniform estimate, which is already up there. And then I have a q to the minus d1, but I also, we have numerators, a up to q, so there is a plus 1. I don't care at all about the exponential, and remember when you integrate in tau, you get forget the normalizing factor. You get the integral when you integrate that tau epsilon plus tau to the minus d over 2, the main contribution coming when tau is less than epsilon, it just gives you epsilon to the minus d over 2 plus 1, which cancels out with the normalizing factor because epsilon is 2 to the minus 2k and to the minus 2. So these two cancel out. And now we will use that little lemma. When q does not divide qj, then we are equal d over 2 minus 1, which is still bigger than 1, that is 5. So we will get 2 to the minus j, d over 2 minus 2, j to the minus 1, which is less than 2 to the minus j half, j to the minus 1, because d is at least 5. So that's exactly the estimate we want. And here we didn't use anything new, just a little bit of lemma there, that you get a little bit of extra cancellation we will need. So that there is nothing new here. The second sum is coming when you decompose the range of integration into two parts. And original integration is going from basically 0 to infinity in tau, 0 to actually not infinity, but we didn't care the right endpoint. But the second is coming when you integrate only on on a larger range. Then tau is much bigger than epsilon, so you integrate only there. So, and again, we won't use anything new, we just notice that in this case, we gain the integration. So, in this, so we basically, in the second case, you would divide Qj, but we decompose the integration into two parts.
So I'm a little bit lost. So we are integrating with respect to tau?
Yes, because
because you were talking about the left-hand side is being less than, and then we have an integration in
so you
t.
integrate in t, but t is a over q plus tau on each interval.
Oh,
so when you are,
I see.
So when you integrate on this interval, which is kind of centered at a over q, not quite centered, and then the variable on this is tau.
I see.
And this could be
so
much
you change the variable.
Even on this interval, it could be much bigger than epsilon, because k epsilon is 2 to the minus 2k, and then this 2 to the j is like logarithmically small with respect to it. But then the integral and tau is bigger than 2 to the j over 2 epsilon. Of course, here, of course, tau is this epsilon doesn't really matter, and then you would get an extra factor of 2 to the minus j over 2, d over 2 to the minus 1, epsilon to the minus d over 2 plus 1, which is the previous factor, and this is the gain. And how much gain do we get? This is at least 3/2. So this is less than equal than 2 to the minus 3j over 4, 1/2 times 3/2, epsilon to the minus 0 over 2 plus 1. This cancels out with the normalizing factor, so the contribution would be this, which is less than that. So these are the two easy cases, and we didn't use anything. So the remaining case is the important one when Q divides Qj, and tau is not that much bigger than epsilon. And here we will use the formula which is up there. So maybe I put it down to see. And basically, up to this very small error, this is like 2 to the minus k over 2, up to this error, you can estimate GTX and by just this one term, where this is the fractional part of Q times C. Now, if we are not in this region, because now we are integrating this product, which means that you're restricted to the complement of this region, you have a lower bound on the fractional part of Q times C. So if C is not in omega jk, then what do we have is that cube C divided by Q, which is C minus some L0 where Q, that L0 is just the fractional part of cube C. And for this one, we have that this is bigger than equal than 2 to the minus k minus j. So that was a mistake here. So then, now we can estimate the exponent here. How large will it be? And So we look at this exponent, and if we have this estimate, then we would have that this exponent would be pretty large, would be as big as 2 to the j. And we get the double exponential gain, we don't even need that, so let's see. So then epsilon, or epsilon squared tau squared, let me put it this way, qc squared over q squared would be bigger. So how large is epsilon? Well, that's 2 to the minus 2k. Tau squared is at most 2 to the j over 2 epsilon. So the denominator is bounded by 2 to the j epsilon squared. So this will be bigger than epsilon, 2 to the j epsilon squared, times the square of that. So 2 to the minus 2k minus 2j, so maybe I write this 2 to the j minus k, so that's 2 to the 2j minus 2k. So this is epsilon over 2 to the j, epsilon to the minus 1 over 2 to the j, and epsilon to the minus 1 is 2 to the 2k. Remember that epsilon is 2 would be minus 2k. So what we have, epsilon to the minus 1 over 2 to over
Minus
epsilon to
two.
the minus 1 is 2 to the 2k over 2 to the j times 2 to the 2j minus 2k. So these cancel out and you get 2 to the j. So we get an extremely small term here. Instead of 1, we get e to the So before that, we assume this is bounded by 1, but now this will be bounded by e to the minus c to the j. Of course, this is much smaller than 2 to the minus j r j to the minus 1. So we kind of overshoot in this decomposition, but you can't really gain anything more than that because of the S1 sum. Now, there is a little bit of cheating here because why do I have this estimate? I have that I'm away from qj, but of course, c minus L0 over q, you can always write it something like c minus L1 over qj, because q divides qj. So here let me use the fact that, that q divides qj. So, and then you would have this estimate. So that's why we take the least common multiple, so that no matter which q we use, we would be away from it, at least this much. So then we have a huge extra gain. So in all 3 cases, we have this gain. So once we have this kind of concentration, how can we use to go from one scale to the full maximal function? That's kind of a usual type of resolution in of the Fourier transform. So basically, we see, so originally we never used anything about this exponential term here, because this would be 0. And if this is 0, you have no gain. But immediately, if this is a little bit away from bigger than 0, then you can get a large gain. So that's what we use here. Okay, so exploit this. So basically, so let's first introduce a smooth version of these omega j case cells. So these are basically neighborhoods of a grid of 1 over qj of very of a certain very small size. So in general, if I want to define a smooth version of a neighborhood of a grid of size 1 over Q, and then you put small little q plus size 1 over L around each point, and you define a function whose Fourier transform is essentially just a smooth version of this neighborhood. So for Q, connection number Q and L, which is much bigger than Q, define the following function. First of all, let's just start a Schwarz function such that the Fourier transform is a cutoff function. So its Fourier transform looks like this. So let's say one or unit Q indicator function of the unit could be less than equal of the continuous Fourier transform less than equal, let's say 2 times unit Q. So it's a standard Fourier transform is a standard cutoff function that doesn't make psi. You cannot make psi positive, but we won't need that. Just a smooth function and define psi QL. Now, on the integer of the left is the following function. So that psi QLM to be equal to L over Q to the minus V times psi M over L if M is in QZ to the D, so if each coordinate of M is divisible by Q and 0 otherwise. So if something like a normalized function of psi, but just inside a grid, but the point is it was some summation, which I won't explain. If you take its Fourier transform and you calculate it with Poisson summation, it would be the following. It would be a sum L all through Z to the D, the continuous Fourier transform of psi of L times C minus L over Q. And that's exactly the type of function we want, because here you sum for each lattice point of each point of the grid of 1 over Q. So this L over Q gives you exactly these grid points. And then you multiply it with L. And then because psi hat is like a cutoff function, it would be just these cutoff functions around these lattice points. So let's believe that. So this is basically just a smooth Fourier transform, a smooth version of these neighborhoods. And now we set this up to work without parameters. So moreover, write psi jk hat to be psi, and now L, our scale would be 2 to the j minus k, and Q would be qj. So j 2 to the k minus j. So that's exactly the smooth. So basically, this is the smooth version of these neighborhoods of the indicator function of omega jk. So we use these functions. Okay, and now what we will do, we kind of play with both parameters k and j, and we will do a resolution around each lattice point and kind of put using these gains, we kind of put together all these estimates, what we get for the different pieces. So let's try to prove now the full two spherical maximas theorem. So what we want to prove is the following, which I don't know. So this is the special case of our main theorem. Basically, it says that if b bigger than or equal to 5, F is in L2 Z, then the discrete spherical maximal operator apply to F. L2, as the equal constant times L2, where a star F is the sum of F star sigma lambda, but for all positive lambda, of course, for which lambda square is an integer. So that's what we want to prove. So the proof would be the following, based on the following resolution. So K would be bigger than some constant. So let's say so. Of course, and we would use this mk of f for a to the k star f. Notice that a star f is bounded by the suit in k and k of f, because basically if you take the suit for all k and then lambda for all lambda between 2 to the k and 2 to the k plus 1, then you get the suit over all lambda. And in a discrete case, of course, you can restrict when the lambda is bigger than a constant. Okay, so for each k, we will do a resolution of the Fourier transform of f. Okay, so for given k, let's write the following way. So let's write f hat to be f hat times psi k 0 hat plus sum of j going from 0 to jk minus 1, where this j sub k would be log to k, maybe minus a constant, of sine k f j plus 1 minus sine k f j, which we will denote by delta sine k of j, plus the last term. So this is just a telescopic sum, and the last term is 1 minus sine k of jk. So according in the original space, this is a decomposition into convolutions. So in the original space, you have a decomposition of f into f star by k0 plus some j is going from 0 to this fixed number jk of f convolution with delta sine kj, plus the last term is f minus f convolution into sine k of jk. Okay, so now we want to apply the maximum operator to these terms separately, and for each one we want to show that each one is bounded by a constant times the epsilon of f. Now the first term, what is this psi k0? So this means q equal 1, but this psi k0 is basically nothing else. So that's the first observation. So remember that that is just 1 over, so that corresponds to q equal 1, to the 0 is 1, or by convention we define this to be, and this is just 1 over L to the d of the indicator function of actually 2 to the k, L is 2 to the k because j equals 0. So L is 2 to the k minus j, which is 2 to the k. So it's just the normalized characteristic function of the cube of size 2 to the k. So corresponding in the definition when L is 2 to the k and q is 1. So now, if you apply a spherical average to this, that the radius is about 2 to the k, nothing really happens. So uniformly, you would have that on one scale, would be just basically bounded by the maximum averages over all Q, which is just a standard Hardy-Littlewood maximal function, as denoted by F after Hardy-Littlewood. And that is uniformly of course, here we can assume that that is non-negative because we are looking at the positive operators of so that means since this is uniform in K, so then even you can even take the supremum, so you will get that A star so you can say that the sup in K and K F star psi K 0 is still bounded by the Hardy-Littlewood maximal function, so the L2 norm of that is bounded by the L2 norm of F itself. So the first piece of the resolution is just basically bounded by the standard Hardy-Littlewood maximal function, that's fine. And the other easy case is the last piece where we will see how do we use the length. Because now we can use the lemma, because if I consider the maximal function, so this is the maximum taken over radius roughly 2 to the k. But now I apply to the last piece. So the Fourier transform of this is supported in omega k jk complement. Because the Fourier transform is 1 minus psi hat, and psi hat is concentrated. Psi hat is 1 on omega j, omega k and jk. Because that's how we set up these signs. So then this would be bounded by our lemma 2.1 is so we would have again 2 to the minus jk over 2 and jk to the minus 1 at 2. And remember what is this jk? That is basically log 2 of k. So that is bounded by k to the minus 1 times k to the minus 1/2 log k to the minus. Now then the sup is, of course, then you can use a square function estimate. So if you take the sup of k and k, f minus f star, psi k jk, L2 norm, as usual, that is bounded by the sum k and k applied to the function. The square, then you integrate, you take the square to the 1/2, and that is bounded by the sum of these terms, so that is sum of k to the minus 1 log k to the minus 2 times f naught 2, and this is bounded because of log k factor. So this is where we would need this extra little piece Of course, if you have higher dimensions of k to the minus 3, the higher power, and you don't need this, you only need this log k in dimension 5. Because then indeed here just you have a 1/2 power, d minus 2 over 2 is 1/2. d over 2 minus 2 is 1/2. So these are the first and the last species, and for the middle space, you have a basically again the user square function estimate and Minkowski to interchange the sum in j and k and use the decay again, because the Fourier transform of these species are again away from those little neighborhood ground rationals. So for each one, we would have a little gain in j. So we just have to interchange the summation in j and k. Maybe I'm over, so I will leave this next time to finish this argument, and then I will change topics and I will talk about active distribution and some Ramsey-type results, but I will use in both cases the maximal function theorem, so it will remain, it will play a role in the other topics as well. Unfortunately, I could not finish, but I will recap next time where I start.
Thank you. Questions, comment? Please.
Could you repeat this
Which one?
for psi k0?
Oh, yeah. How does that work? So basically what happens here is, it is not true, so this is kind of moral because it's a Schwartz function. But more or less it is, so it is a Schwartz function, but kind of constant on scale 2 to the k. So when you take such a function, an average with lambdas, which is about 2 to the k, basically the average doesn't do much to the function, so it will be estimated uniformly for all lambdas between 2 to the k by just itself. So basically then this maximum operator would be estimated by some average of f, basically the average of scale 2 to the k, but if I want a uniform estimate, I include all averages, and that would be the hard little maximal function when you take all averages. So basically my use the maximum function to get this uniform estimate. For all k, it's estimated by average at some scale, and the soup of average at no scale is what is called a hard little maximal function. So that's why I have this estimate. And of course, the soup k of mk is the average over radii, because for every k, mk includes all the radii between 2 to the k and 2 to the k plus 1, and it will take all the averages. So that is that's why you start the resolution and this way.
Other comments or questions? Okay, so thank you also for the model. Let's make a brief